Module prepared by Professor Ahmed Datta, School of Business, George Mason University. In this module, we will discuss a forecasting technique, a very popular one called exponential smoothing. So I'll first show you the mechanics of how it's done, and then towards the end, we'll spend a few minutes discussing why this method is called exponential smoothing. So to start off, let's put ourselves in a position where we have to make sales forecasts. So imagine that we are in week one, right over here, we're in week one, and in week one, we actually have sales of 17 units. Okay, so there is nothing to forecast really for period one. So just as a default, let's say my forecasted value for period one is also 17 because I know it to be 17. That's what it is now. So the issue now is I have to make a forecast for period two. So my forecast for period two, here's the logic behind the forecast. So my forecast for period two is a weighted average of what I actually observed in period one and what I forecast for period one. And how much I weight one over the other is controlled by this parameter alpha. Okay, so let's do the computation and we'll come back and explain it once more. So my forecast for period two is equal to 0.2, which is the alpha, times the actual sales that I saw in period one, plus zero point 0.8. Where did the zero point 0.8 come from? It's 1 minus alpha, 1 minus 0.2. It's 0.8 times the value that I had forecast for period one. Okay, so you can see below the formula that I have written. Ft plus 1 is equal to alpha times yt plus 1 minus alpha times f of t. Or in plain English, the forecast for period t plus 1 is equal to alpha times the actual value of sales that I saw for period t plus 1 minus alpha times my forecast for period t. Okay, so here we have my forecast for period 2, which is also 17. That's what you would expect given the numbers there. Now let's see what we actually observe in period 2. So let me uncover this data. Well, now I forecast a sales value of 17 and the actual sales was 21. So based on these two numbers, what would my forecast be for period 3? Exponential smoothing says once again, my forecast for period 3 would be 0.2 times the actual value of sales that I saw in period 2 plus 0.8. 0.8 is the 1 minus 0.2 multiplied by my forecast for period 2. Okay, so my forecast for period 3 is 17.8. Now what do we actually observe in period 3? Let me uncover this. This is 19. So I'm a little bit off. Okay, so the same logic would follow for period 4 and so forth. So instead of doing this manually for each cell individually, let me copy the formula down. These are my forecasts, and of course let me take away the mystery here. These are the actual values. Okay, so I've shown you the mechanics of how one goes about doing exponential smoothing. Okay, and you can see that the forecasted values don't bounce around as much as the actual value of sales. We'll see that in the graph in just a little bit, but uh, you can see that the parameter alpha controls how much weight I give to the actual current observation. If alpha is close to 1, then I'm giving a lot of weight to the value of sales the most recent value of sales that I observe. Okay, if alpha is closer to 0, then I'm not giving a lot of weight to what I actually observe. All right. So you would expect that when alpha is small, meaning close to 0, the forecast would be pretty damp. It would not wiggle around so much. It would not match the actual fluctuation so much. Whereas if alpha is high, which is closer to 1, then you are more reactionary. You react much more quickly to changes that you actually observe, and the forecast would fluctuate a lot more. So let me repeat these numerics for column D and column E. Fortunately, you will not have to do these calculations manually. I'm just showing them to you manually first to see the mechanics of the calculation, and then there's a built-in function in Excel. To do that, there is one little idiosyncrasy that we'll have to worry about, but we'll deal with it once we get there. So for alpha equal to 0.4, again, the starting point for period 1 is 17. So I know the observation of actual sales in period 1 is 17, hence there's nothing to forecast. So default, my forecast for period 1 is 17 here as well. So now the interesting thing starts is from period 2, what is my forecast for period 2? This would be equal to 0.4 times the actual value of sales that I observed in period 1 plus zero point 0.6. Where did the 0.6 come from? It's 1 minus the 0.4 times the value that I forecast for period 1. Okay, so I simply copy this formula down, and these are my forecasts for the 12 periods based on an alpha or a weighting factor of 0.4. Similarly, if I use a weighting of 0.8 for the most recent observation, so my starting point once again is 17 for period 1. My forecast for period 2 would be 0.8 times the actual value of sales in period 1 plus zero point 0.2, which is 1 minus 0.8, multiplied by the value that I forecast for period 1. And I copy this formula down for all the different cells. And here you have 3 different forecasts based on 3 different weights. Again, informally, what would I expect? I expect that when alpha is equal to 0.2, that I'm not reacting strongly to actual observations. So the forecast with alpha equal to 0.2 should be much more damp compared to the forecast with alpha equal to 0.8. Let's see if that is actually indeed the case. So I've plotted these forecasts for you. Let me look at the graphs. Now, if you look at the graphs over here, the blue line is the actual value of sales. The brown line is with alpha equal to 0.2, and the violet line is for alpha equal to 0.8. And you can observe that the violet line swings around much more and reacts much more rapidly to actual value of sales compared to the brown line. The brown line is much more damp, as you would expect. Okay, and in fact, this is what Excel does. This is the little idiosyncrasy in Excel you'll have to deal with. So let me reproduce these 3 columns again using the built-in functions in Excel. So I would go to data analysis, and I would pick up exponential smoothing. Okay, so you can see that the input range is specified as column B. Okay, and to reproduce alpha equal to 0.2, this is the little idiosyncrasy you'll have to be aware of. So in Excel, in order to reproduce the column corresponding to alpha equal to 0.2, I would have to put in a damping factor of 0.8. So what Excel calls the damping factor of 0.8 is corresponds to our alpha equal to 0.2. Now the output will be exactly the same. So I want the output to be put over here. Okay, that's why I wrote D equal to 0.8. So D equal to 0.8 corresponds to alpha equal to 0.2. So here's the output, and let me fix the decimal points over here. So you can see that the numbers in column C have been reproduced exactly using that built-in function. Similarly, to reproduce column D, I would again go to Excel, do data analysis, exponential smoothing. Everything remains the same. The damping factor, I would need to put in 0.6, which is 1 minus the alpha of 0.4. And the output range I would give as this one, H2. And there you have the output. Let me again fix the decimal points to 2 decimal places, and there you have it. Is the exact reproduction of the numbers in column D. And the last, I will do it for alpha equal to 0.8. So let me do this quickly. I would have to put in a damping factor of 0.2, and the output would be in cell I2. So there you have a reproduction, exact reproduction of the numbers in column E. So this is what you would do mechanically in Excel, but I wanted to show you manually first. Okay. Now, as I promised, we'd spend a couple of minutes just explaining why this method is called exponential smoothing. Just as a reference, remember this formula over here. So what it's saying is the forecast for period t plus 1 is equal to alpha times the actual observation for period t plus 1 minus alpha, the forecasted value for period t. Okay, so here I shift to a next sheet. So here's the formula. F of t plus 1 is equal to alpha of yt times 1 minus alpha f of t. So just take the f of t, the forecasted value of t, and plug in the formula for f of t, which is alpha times yt minus 1 plus 1 minus alpha f of t minus 1. Okay, so if we expand this expression to save us a little time, if you come to this little expression over here at the end, which is equal to alpha times yt plus 1 minus alpha times alpha yt minus 1, etc., etc. We don't need to go into the math, but all I want you to do is focus on the pattern of the coefficients. So my forecast for period t plus 1 is equal to alpha times the actual observed value in period t plus a smaller coefficient multiplied by the value observed in period t minus 1 plus an even smaller coefficient times the value actually observed for sales in period t minus 2, and so forth and so forth. So the coefficients decay exponentially, and that is why this method is called exponential smoothing. Okay, fortunately there's a built-in function in Excel to do this, so you don't have to do the calculations manually, but I wanted to show you both the logic behind the calculations as well as the impact of the damping factor. So when you are doing the forecasting, what you will have to really choose is what is the appropriate damping factor that should be used for your analysis and forecasting.